problem 7. Okay. Consider a uniform flow past a cylinder with a V-shaped wake as shown. Pressures at 1 and 2 are equal. Let B be the width into the paper. Find a formula for the force F on the cylinder due to the flow. Also compute the drag coefficient CD, which is defined by CD equals to F over rho U squared times L times B. Okay, so first what we want to find here, we want to find the interactive force between the cylinder and the flow. Okay, you know that if you find the force of the cylinder on the flow, it will be opposite to the force of the flow on the cylinder. Okay, so if you take as control volume your flow, because you know, so if I want to draw it here, you can take it like this. You take the control volume, so it will include the streamlines developing around the cylinder, and it will include, of course, the inlet and the outlet. Okay, so of course the cylinder here is not a part of the control volume. So here, if you want, my control volume will be like this, and it will not include the cylinder. So I will remove the cylinder. Why? Because I want to find the interaction between the cylinder and my flow. Okay, so your control volume is not including the cylinder here, the shape here. Okay, now we want to find the force of the cylinder on the flow. Then we can deduce the force of the flow on the cylinder. Okay, now what we will do here, because you are interested in a force, what should we apply? When you always when they ask you about a force, think about conservation of momentum. Okay, so I need to apply conservation of momentum for this control volume. I know the inlet, I have a uniform inlet. What I mean by uniform is that the velocity is the same everywhere on my inlet, while for my outlet it's not the case, because as you can see, the velocity at the outlet is varying. Okay, so of course if you want the limit of the control volume, I mean just here if you want, because here it's an outflow. Okay, so what I want to do now, I will apply the principle of conservation of linear conservation of momentum, and I will apply my equation. In which direction I will apply my equation? Your flow is in which direction here? If I call yes, if I call this direction x, so my x-axis, I will take my x-axis like this. This is my positive x-axis. Okay, so I will apply the conservation of momentum in x direction. Now,
Doctor, can you please admit me from my laptop?
Sorry?
Can you please accept me from my laptop?
Yes, like 1 minute, but I cannot. Okay, yeah. Okay, so now along x direction, first they told me that pressures are equal. Okay, I have equal pressure on my system. So whenever you have equal pressures everywhere, no need to. When you have equal pressure everywhere, no need to do anything for the pressure. So the pressure is maintained, it will cancel out from all sides because you have the same pressure everywhere. Okay, since you have the same pressure everywhere on your control volume, no need to consider pressure forces because they will cancel out. When you need to consider pressure forces, when you have different pressures. Okay, so as we have seen last time when we did the example, you have everywhere the atmospherical pressure. Only on the inlet and outlet you have different pressures. This is why we considered in the last problem at the inlet P1 minus PA, and at the outlet P2 minus PA. But here, since they told us that the pressures are equal, so no pressure forces. Okay. Now we have only the effect of the cylinder on the flow. Okay. So when we want to do, if you want, you can do some analysis. How will be this force? It will be to the right or to the left?
Should we take the weight?
The weight, look here, if when they don't mention anything here, maybe it's a horizontal plane. And even if they don't mention anything, you can neglect the weight. Okay? When they don't give you information, you can neglect the weight. Okay? But here
دكتور بس شو مشان conservation of momentum؟
شو يعني conservation of momentum? Of linear momentum. يعني when you apply, if you remember, if you have studied the material, when you apply Reynolds transport theorem, you can apply it on mass, you get the continuity equation. You can apply it on velocity, you get the conservation of momentum. What is linear momentum is mv, okay? And when you apply Reynolds transport theorem, you will obtain an equation on conservation of momentum rate over your control volume. So we call it conservation of momentum. You can apply it in X, you can apply it in Y. Okay, you can apply it if you have 3D, you can apply it in X, Y, and Z. So here, the conservation of momentum will tell us why, because it's a steady application here, then the term of derivative with respect to time is 0. Okay, so what do we have only? We can say that sum of forces on my control volume
البادي وفي surfaces. البادي ما عندنا اياه صح؟
مظبوط، ما عندنا البادي because it's steady state. اوكي، فعندنا بس السيرفيسز. so it's
ما عندنا البادي عشان مش عاطينا الويت صح ولا لا؟
you mean body forces.
body forces و surface forces.
yes انا فكرت قصدك شيء ثاني. اوكي
لا الريت لانه steady state ما بنستعملها.
yes I mean body with surface, but yes. So here
control surface integral of V rho
yes,
V
exactly. So here if you want the weight we neglected. أصلا it might be a horizontal plane. They didn't give information if it's a horizontal plane or a vertical plane. So anyway, even if it's a vertical plane and they don't give us information, we can say that the effect of the weight is negligible compared to the other forces. Okay.
Okay.
And keep in mind also, even if you have the weight, let's say the weight is not negligible, the weight will be in which direction?
It will be in the y direction.
Yes, it will be in the y direction, so it will not affect the equation in x. Okay. Yes. So even if you have a weight, the weight you should account for it when you apply for conservation of momentum in y direction. And here, of course, you will have a certain support that will oppose the weight, because as you can see here, as the water will flow, it's not going down because you have a certain support which will not allow it to go down. Okay. So in all cases, the weight will be opposed by something. So and since we are concerned in x direction, so even if the weight is not negligible, we will not take it into consideration. Okay.
Doctor?
Yes.
Here, why did we neglect the derivative with respect to time? The term.
We didn't neglect, but it's a steady state application.
Zero.
When they don't mention, when you don't have u function of time, as you can see here, the profiles of velocity are not changing with time. Okay. You have a uniform flow at the inlet, and at the outlet, you have a profile that is independent of time. As your profiles at the inlet and outlet are independent of time, then you can say that I don't have a problem. Okay, so I don't have a transient application, it's steady state. So del by del t will cancel out directly. Okay, so I will only end up with two terms. What are the two terms? Integral over the control surface. Okay, so if you want, we can go to the formula sheet. I prepared for you a formula sheet that can help you in solving problems of this chapter. Let me show you the equations we are using. I should share my screen because not only 1 second. Do you see now the formula sheet I prepared for you?
Yes.
Okay.
Yes.
So here, what we are applying now is here. We are talking about conservation of linear momentum. The general rule for conservation of linear momentum is that sum of forces, and here you will take all external forces acting on your control volume. You will include pressure forces, viscous forces, weight force, gravitational force. We mean by this the weight, for example. We have surface tension, any type of forces that are applied on my control volume, I should take into consideration. Okay, but pay attention always also to project your forces. So here, because I am considering x direction, so even if the weight is not negligible, it will not affect my equation in x. Now, the second term represents the momentum accumulation or loss in the control volume. And
هيدا اللي
here,
حسبناه زيرو.
هذا حنحسبه zero because it's a steady
Okay.
state application, so we will not account for this term. We still have the second term, which is integral over the control surface of rho v, okay, times v relative dot nda. Just pay attention for something. You have two cases. You can have a fixed control volume, okay, and you can have a moving control volume. Until now, we have considered problem with a fixed control volume, but after we will also consider moving control volume. What is the difference? The only difference is that when your control volume is moving, when you calculate m dot, you should do vr dot n, okay? So you take v relative dot n, not the absolute velocity, because you, for example, if you have a car that is moving at a certain velocity, let's say it's moving at 5 meters per second, for example. It's moving at 5 meters per second. And you have a jet that is trying to enter the car at 10 meters per second. The actual velocity relative to the car will be how much?
Five.
So when you want to calculate m dot going inside the car, which velocity you should consider? You should consider 10 or what?
Doctor, the relative velocity of what
Five.
with respect to what?
Yes,
Relative
Five.
to the
Five.
car.
you should consider 5. Exactly. Because imagine that the water jet was of velocity 5 meters per second. It will not be able to enter the car. To enter the car, the velocity of the jet should be higher than the car velocity. So when you want here to calculate m dot n, okay, you should do rho times area, cross-sectional area, times what? Times v relative. What we mean by v relative, it's the velocity of the jet relative to the car. So it's equal to rho times a times 5, not 10, okay? So in general, this is a general formula. If your control volume is fixed, then v relative is equal to the velocity, okay? And if in case it is your control volume is moving, when you compute m dot, you should not forget to do here, as here, for example, 10 minus 5, and take into consideration relative velocity, okay? So now,
Doctor, just to be sure, هي the relative velocity of the jet with respect to the car, right?
yes, of course, of the jet
Okay,
with
that's
respect to the car, yeah. Okay, now, here, for this term, what do we have? Vr dot nda represent what? This term is simply or plus m dot or minus m dot. This term is equal to plus m dot, in which case, in which you have an outlet, okay? When you have an
دكتور بس
outlet,
ليش قلنا دي باي دي تي ايكوال زيرو بس قبل شوي؟
لأنه it's steady state. يعني the profile of velocity على الانlet والoutlet are not changing with time, okay? Did they give you function of time for inlet velocity or outlet velocity? No.
نو
No, so nothing is changing with time. If you don't have a function of time, this means that you are dealing with a steady state case. And in this case, del by del t will cancel out. The term of variation with time will cancel out. So you have only to compute this term, okay? Now, Vr dot nda is equal to plus dm dot, okay? In case it's an outlet, and is equal to minus dm dot in case of an inlet. This is why in general directly when you have uniform flow, you can directly, you don't have to deal with an integration, okay? You can directly say that it's plus m dot out u out minus, of course, we should have the rho with it, okay? So rho times Vr dot nda is m dot. This term plus this term. If you just take this term, it's the elementary flow rate. When you multiply it by rho, you get a plus dm dot outlet if it's an outlet and minus dm dot if it's an inlet. Now, pay attention. If you have a uniform profile, no need for integration. Why? Because if you have a uniform profile, then what about this term V? This is the velocity of your flow. If you have uniform flow, V is constant over your inlet or outlet, then no need to integrate. So when V is constant, so I will write it here. When V constant, no need for integration. No need for integration. This is why when you have uniform outlet or inlet, you say it's plus m dot out u out, okay? And if it's an inlet, it is minus m dot in un, okay? Now, the problem is if I don't have a uniform profile. If I don't have a uniform profile, I should do integration, okay? Because if V is variable over the control surface, I should do integration to calculate this thing. Let us see in the example we have how to do the integration. So let us go back to the problem. Okay, here. For the inlet, no problem for me because it's uniform, okay? So when I will write my equation along x, I will write that sum of forces in x is equal first. For the inlet, it's minus m dot
دكتور بس سؤال ما خصه
Yes.
باللي عم تحكيه.
نعم.
شو V shaped wake؟
V-shaped wake is, look, when you have a flow over a body, this will form a zone, a wake zone. We mean by this a zone where you have circulation, where you don't have flow due to separation. So here, look at your streamlines. When the flow will face your rigid body, then your streamlines will do separation here, okay? So just at the rigid body level, they will separate. Here you have what is called a wake zone because you have, if you want separation of flow and the velocity will not be uniform here. And just after the cylinder, you have what we call, this is called a wake region. And just after a certain distance, your flow will be developed again and will have a certain profile. And this profile variation here is due to the wake zone. So this is why it's not uniform, because the cylinder will affect the flow field. And this is why here directly after the cylinder, you have smaller velocity and it will increase until reaching again the value u, okay? So here you have like the boundary layers, it's like the formation of boundary layers. Here you have, when you have a flow hitting an object, you have separation and you have formation of a wake zone, okay? Let me check in the chats. Okay, now
Yes مش الحال.
okay, so as we said, what are the forces acting on the system? We only have the effect of the cylinder on the flow, okay? And the force of the cylinder on the flow will be to the right or to the left, do you think?
Left.
Left. Why? Because the flow is trying to pull the cylinder to the right. So by action reaction, the cylinder will try to do a resultant force on the flow to the left. So here I will put, this is the force of the cylinder on the flow. Okay. Now, and as we said, for pressure forces, they cancel out, and The weight is in vertical direction, so no need to put it. So now I will say that sum of forces in X, I only have the drag force. So because it's to the left, so it's minus force of a cylinder on flow. And you know that by principle of action reaction, it's equal to plus.
دكتور بس ليش left مش right؟
ليش left؟ لأنه الفلو على السلندر is to the right, but the cylinder on the flow will be opposite. Okay? يعني أنت the flow is going to the right, so it's trying to pull the cylinder towards the right. Yes or not?
Yes.
And by action reaction, the cylinder action on the flow will be opposite to the left. Okay? So I have.
دكتور بعد سؤال.
نعم. Yes.
قالوا لي البريشر ايكوال، بس البريشر فورس مش هي البريشر تايمز اريا، بس على ميلة اول ميل الاريا مش اكبر من ثاني ميله.
No, you have the pressure مش بس هون everywhere is the same. يعني هنا they should be clear. The pressure everywhere is the same، مش بس على الانلت والاوتلت، على streamlines also of the limits. يعني here also.
حتى لو الاريا بتتغير ما بيأثر.
ايه هلا انتبه، لو البريشر مش هي ذاتها everywhere بصير معك حق. يعني اذا انت ما عندك same pressure everywhere، okay, then you should اذا بتفرق الاريا حتفرق، بس هون you have everywhere the same pressure, so it will يعني an overall لحية if you take the overall effect of pressure in x direction is equal to 0. okay, لأنه on the whole control volume you have the same pressure everywhere، مثل ما يكون مثلا atmospheric pressure or any pressure. If you have the same pressure everywhere, then you can say that in overall, if I find the resultant along x, it will be 0. Okay?
Okay, ماشي.
So, let us continue here.
دكتور sum of forces along x شو صار بالm dot m dot n u n
يلا
m dot
ما
out u n؟
خلصنا، رح ارجع
اوكي
هلا رح اكتبها equals to. Now, I have an inlet and an outlet. Okay? Because for the inlet I have uniform velocity, I can, and it's an inlet, I can directly put minus m dot inlet times u inlet. Okay? And what is u inlet? It is big U. Okay? Now for the outlet, directly when it's an outlet you put plus. Okay? Now plus integral of what? As we have seen in the formula sheet, integral of, now since you are applying in x direction, then you directly put rho times v component along x. Okay? So rho vx times, or if you want, since we can take rho with m dot, we can simplify rho and put here d elementary, I mean by d elementary, very small, d m dot out. Okay? D m dot out. Okay? Now how to compute elementary m dot out? How to compute it? Okay? You know that m in general, how you calculate m? Mass flow rate m dot. M dot is rho times area times velocity. Okay? But here, since the velocity is not uniform over your outlet, you will take elementary m dot. Okay? D m dot equals to rho. What will be your area? You will take an elementary area dA, okay, and you will multiply it by velocity u at the corresponding location. Now, what is the elementary area dA? Look, this is your outlet. This is your outlet, okay? If you look at the profile, I will draw it here for you again. This is your outlet, and this is your velocity profile. Your velocity profile is symmetrical with respect to the center line. So as you can see, u is function of y in your problem. So if I consider this is an axis, I will call this axis y. So your velocity u will be function of what? Is a function of y. Okay? And if you want to take an elementary area of your flow, since here you have constant width, b, then if I take a very small thickness dy, so I will take any location y. Okay, let us say here, if I consider here, at this level, the velocity is, I will call it u of y. So this is u of y, function of y, okay? And I will take the elementary area of a small thickness. So I will take a very small thickness here.
اعطونا thickness B.
لا انتبهوا علي، thickness B بس قصدي ما انت بدك تاخذ elementary area هتاخذ thickness B times what? Times a very small variation of y. يعني dy. Why you are doing this? Because the velocity is changing. فانت بدك تاخذ a very small element where the velocity is not changing. If you want to take a very small element for which the velocity is the same, with width ما عم يتغير البروفايل. Okay, with width you have same velocity. So your elementary area will be this one. Your elementary area dA will be equal to what? Will be equal to a very small thickness dy times the width, which is b. Okay, so now in this equation you can replace dA by what? So you have equal to rho times u is a function of y, okay, times dA. What is dA? It's b dy. So as you can see here, what we did, we have now to integrate a function that is just function of y, because as you can see here, I can find u function of y in my problem, because u is only varying in y direction. Now, how to find the variation of u with y? I need an equation, okay? How can I write my equation? It's very simple. If you look, let me erase everything so that it will be clear for you. Look, what I know is that for y equals 0 at the center line here, for y equals 0, the velocity is equal to u over 2. And for y equal to L, the velocity is equal to big U, okay? So I have 2 points for this variation. I can say that for y equals to 0, I have that the velocity u is equal to big U over 2. And for y equal to big L, I have that u is equal to big U. Okay, so now what will be your what will be your function, u function of y? It's a linear profile. Okay, so it is of the following form: uy is equal, it's a linear variation, it's equal to ay plus a certain constant. A is the slope. Okay, how you find the slope of a linear variation? It's delta u over delta y. So the slope A is simply equal to delta u over delta y. It's equal to, the variation in u is u over 2. Yes.
مش هيدا هي دلتا واي على دلتا يو.
لا، ما انت بدك تجيب u function of y. مظبوط.
اوكي صح.
Okay, so it's u over 2 over dy is L. Okay, so it's over 2L. Okay, this is the slope. Now to find your constant c, you can simply say that for y equals 0, you replace. Okay, for y equals to 0, I have that u is equal to big U. So big U is equal to u over 2L u times 0, so it's directly 0. Okay, so u over 2 is equal to the constant c. So now I have the equation. Now I can say that u function of y is simply equal to u over 2L u over 2L times y plus u over 2. Okay, and if you want, you can take u over 2 as a factor. So you get that your function is u over 2 times y over L, y over L plus 1. Okay. Let me check your questions. Hadi, which idea you mean? The profile? Hadi, do you hear me? You are telling me to repeat the, okay, the profile. Okay. I will repeat the idea. Look, whenever you have a flow that is variable, so you don't have uniform profile, you need to do integration, okay? Because when u is variable and you want to compute integral rho v times vr dot nda, okay? So you need to do integration because you know that when I have a function that is variable and I have integral, I cannot take outside of the integration because it's a function, okay? So the first step to do to be able to do your integration, you should find u as a function of y. So if you look at your figure, you have that the velocity profile is given. It's a linear profile. The velocity is increasing. This is, we consider the y-axis like this, okay? This is the origin of the y-axis. So you can say that for y equal to 0, what is the velocity? At this level, the velocity is equal to u over 2, okay? And for a certain height L, I know that the velocity will reach a value equal to u. So it's a linear variation, and I know 2 points. For y equal 0, u equal to big U over 2. And for y equal L, I have u equal to big U. So all I have to do here is to find the equation of the line, okay? For a line, what is the general equation? It's a slope times y plus a constant. To find the slope, you do delta u over delta y. Since you have 2 points here, you do u of 0.2, which is u, minus u over 2. It will give you u over 2. Then you divide by delta y, which is L minus 0. It's over L. So you get that your slope is u over 2L. Okay? Then, to find your constant c, you can use any of the 2 points. Or you replace for y equals 0, u equal to big U over 2. Or you replace that for y equal L, small u equals to big U. Then you can get your constant c. Okay? And after this, when you get the slope and c, you have the equation of the velocity. U function of y is u over 2 times y over L plus 1. Okay, Hadi? It is clear now?
دكتور
Yes?
في أول سؤال لما الفيلوسيتي ما كان عندها linear profile استعملنا نحن فورمولا الكيو اللي هي integral of VR 2 باي ار دي ار. شو الفرق عن هاي؟ ليش هون استعملنا هاي وفوق استعملنا شيء ثاني؟
Exactly, because the shape is different. You should take the cross-sectional area. فوق بالبروبلم اللي عملنا كانت غير دي اي. بالبروبلم قبل اللي عملنا فيه integration كان عندنا circular outlet. اوكي؟ بينما هون كيف الاوتلت تبعنا؟ rectangular. In this problem, your outlet is rectangular. So each time you should treat each problem in a different way. Okay?
دكتور يعني جنرال يعني جنرال لما يكون عندنا سيركل فينا نستعمل تبعية 2 باي ار دي ار، بس إذا أي شيء ثاني بدنا نمشي على الطريقة اللي هلا أنت قلتيها.
Look, تفهمها ما تحفظ شيء. أنت كل بروبلم تطلع فيه شو عم بيصير. بهداك البروبلم الفيلوسيتي كيف كانت عم تتغير؟ With what it was varying? It was varying with radial direction. يعني أعطوك equation function of what? Function of r. مظبوط؟ فأنت for the same r you have the same velocity. منشان هيك كيف أخذت الelementary area وقتها؟ أخذت a sin circle يعني a sin disk if you want. Okay, why أخذنا a sin disk؟ لأنه we can consider that the velocity, since the velocity is only function of the radius, that for a very small thickness along the radial direction, the velocity can be considered the same here. مشان هيك اعتبرنا انه ال dA هي 2 pi r dr. Okay? While in this problem here, ليش قررنا نقسمه in this way in small rectangles? Because the velocity is varying with, in which direction the velocity is varying here? Here the velocity is varying in y. مظبوط? Because it's varying in y, when you want to take an elementary area, you should take the elementary area in a way to have nearly the same velocity over this area. وبما انه الvelocity عم تتغير in y direction, so if you want to choose an area where the velocity is nearly the same, how will be your area? It is a rectangle of width b. Okay, so here you can consider that everywhere in this rectangle I have the same velocity, which is u, which only varies with y. So the elementary area that I should take in this problem is dA equal to b dy. Okay,
اوكي دكتور ثانك يو
so
دكتور
now yes.
بس
Yeah.
بعد سؤال
نعم.
بأسئلة كيف فينا اوقات نفرق بين البرنولي ايكويشن وتبعت الكونسرفيشن اوف انرجي؟ انه وحده بلا اللوسز ووحده مع اللوسز.
اوكي، ما انتو ما هي اذا بدكم الكونسرفيشن اوف انرجي هي كانه particular case من البرنولي مع لوسز. يعني اذا ما في لوسز بتصير conservation of energy.
اوكي
يعني
اوكي دكتور
يعني
ثانك
نحن قبل وقت عملنا برنولي in chapter 3 كنا نعتبر ما في losses، صح؟ لانه بتتذكروا when we derived the equation of Bernoulli ب chapter 3 we assumed what? We assumed no viscous effect، يعني no losses، صح؟ فهلا جينا هون in this chapter عملنا يعني a general rule، وصلنا للجنرال رول اللي هي انه in case we have losses we can account for them into the energy equation by considering the losses.
اوكي دكتور ثانك يو.
دكتور
Yes.
وانا اخذناها ريكتانجل كانه مثل كروس سكشن للاريا كلها، يعني وين
هي
الوتر عم يخبط
هي
يعني احنا بنطلع عليها.
the outlet is a rectangle. Why? Because you have, as I said, you have a constant width into the paper. And if I want to draw the outlet for you here, this is the outlet. Okay? And your outlet is of a rectangular shape. And since the velocity is varying with y, يعني if I take at one level, okay, if I go into depth, the velocity is not varying. The velocity is only varying with height. Okay? So if you take a very small element like this, for this element, the velocity is not changing. You can consider because the thickness is very small, so nearly same velocity here. Okay?
طيب بالسيركل
Doctor, there's less than a minute.
Yeah, I will open a new session. نعم, let's continue. Tell me.
بالسيركل ليش اخذناها 2 باي ار؟ نحن بدنا الاريا.
لانه عملنا 2 باي ار دي ار. انتبه، ما انت اذا عندك سن ديسك كيف تحسب الاريا تبعه؟ البريمتر اللي هو 2 باي ار and then you multiply by the thickness which is dr. Okay, so here this is the elementary area in this case dA, 2 pi r dr, while for the rectangular case it's b times dy.
يعني احنا بدنا السيرفيس اريا كلها من جوا، يعني كأننا بدنا
نحن بدنا الاريا يلي ما عم يتغير عليها الفيلوسيتي، فنقدر نعمل انتجريشن. ما انت وقت تعمل انتجريشن